Welcome to AI Paper Podcasts. We're the place to get up to speed on the latest research, decoded, and ready to use.
Yep, helping you stay ahead.
And today, we're diving into a really interesting one. It's a paper from UC Berkeley called Barbarians at the Gate, How AI is Upending Systems Research. Came out October 9th, 2025.
Yeah, this one's making waves. It's not just talking about AI changing things, it's showing how. It argues AI is automating algorithm discovery in systems research. Stuff we thought only humans could really do well.
Exactly. The big idea they introduce is ADRS, that's AI-driven research for systems.
Right, and the core concept is kind of simple, really. Step one, get an AI, like a large language model, to generate a whole bunch of potential solutions to a systems problem.
Like tons of different algorithms or code snippets.
Exactly. Generate diversity. Then, step two, use a reliable verifier, think a simulator or a real system test bed, to automatically figure out which of those solutions actually works best. Pick the winner.
And they argue systems research, networking, databases, cloud stuff is perfect for this.
It really is. Because verifying performance is pretty straightforward, right? Yeah. You run the code, measure throughput, latency, cost, whatever your metric is. You get a clear number. Simulators make it fast and cheap, too.
Okay, so let's hit the key takeaways right up front for folks maybe listening for a quick summary. This ADRS thing, using frameworks like their OpenEvolve system and powerful LLMs, GPT-4o, Gemini 2.5 Pro are mentioned.
Yeah, those big guns.
It's already beating human state-of-the-art designs, like, significantly.
Yeah, the results are kind of nuts. They got up to a 5.0x runtime improvement for a mixture of experts load balancing. That's huge.
5 times faster. And another one, 49% more cost savings for scheduling spot instances in the cloud compared to the best-known methods.
Which is a notoriously tricky problem.
So the big conclusion, the sort of so what here, is that the researcher's job is changing. It's less about grinding out algorithm code.
And more about the big picture, defining the problem really well, setting the strategy, guiding the AI. That's what we're going to unpack in this deep dive, how it works, the proof, the pitfalls, and what it means for you doing research or engineering in this space.
All right, let's get into that foundation. You mentioned systems research is ideal for ADRS. Why specifically systems? What's the advantage over, say, trying to automate discovering new physics theories?
Well, it comes back to those two core steps.
Yeah.
Generate and verify.
Yeah.
Generating ideas. Maybe LLMs can do that anywhere.
Yeah.
But the verification, that's the key.
Okay.
In physics, verifying a new theory might need decades of experiments or complex mathematical proofs. Subjective interpretation often plays a role in other fields too. But systems performance.
It's concrete. You run the code.
Exactly. Your proposed solution, maybe a new scheduling algorithm or a networking protocol, it's code. You implement it, maybe in a simulator first, maybe straight into the system.
And then you just run it against some standard tests.
Precisely. Predefined workloads. You measure the outcome. Throughput went up, latency went down, cost was reduced. It's objective. Numbers.
And the existence of good simulators is a big deal here.
Oh, huge. It makes the verify step fast and cheap.
Yeah.
The paper mentions running these evolutionary searches, testing hundreds or thousands of AI-generated solutions in just a few hours.
Hours? Wow.
Yeah, and costing maybe tens of dollars in cloud compute or API calls. Compare that to a human researcher spending weeks designing, implementing, testing, debugging.
Right. They actually surveyed PhD students in the paper and found that algorithm design took up about 21.5% of their time.
And evaluation, like running those tests and analyzing results, was another 20.1%.
So over 40% of their time just on that loop?
Basically, yeah. Almost half their research efforts stuck in that generate and verify cycle, but done manually. ADRS aims to just automate that whole chunk.
Freeing up researchers for, well, other things.
For the harder parts, arguably, like figuring out the right problem to solve in the first place.
Okay, so we get why systems is a good fit. Let's talk about how they built this ADRS thing, this OpenEvolve framework. You mentioned it automates the solution and evaluation parts of the traditional research process.
Yeah, if you think of research as having maybe 5 stages: problem formulation, setting up an evaluation framework, designing the solution, running the evaluation, and then writing the paper. ADRS tackles that middle loop, solution and evaluation.
And their figure 3 lays out this architecture. It looks like a cycle.
It is. It's an iterative feedback loop. 5 main pieces working together. You start with a prompt generator.
Okay, what does that do? Is that where the human comes in?
That's a key interface, yeah. The human defines the problem, the goals, maybe some constraints, required APIs. All that goes into the prompt. But it's smarter than just a static prompt.
How so?
It also pulls in context from previous runs, like promising solutions that were generated before, their scores, maybe even feedback on why something didn't work. It builds a really rich prompt to guide the AI better next time.
Got it. So that detailed prompt goes to the solution generator.
Right, and that's where the LLMs live. They mention using an ensemble, mixing different models like GPT-4o for maybe broad exploration, and others like O3 or Gemini 2.5 Pro, maybe for more focused refinement or coding.
So it's not just one magic model.
Probably not. Different models have different strengths. This component takes the prompt and actually generates new code or modifies existing code provided in the prompt.
But generating code, LLMs can hallucinate, make syntax errors, or just write nonsense sometimes. How do they deal with that?
That leads straight to the next piece. The Evaluator. This is that reliable verifier we talked about. It takes the generated code, runs it maybe in a simulator, maybe on hardware.
And it doesn't just say pass-fail.
No, it's more sophisticated.
Right.
It obviously checks for crashes or basic errors.
Right.
But critically, it runs the code against the target workloads, measures the performance metrics defined in the prompt, latency, cost, whatever, and assigns a score. And sometimes they even use another LLM here to provide qualitative feedback if something performs badly. Like instead of just a low score, it might say, "This seems to be stuck in a loop here," or ignoring the deadline constraint. Much more useful for the next iteration.
Right, that feedback would then go back into the prompt generator for the next round.
Well, first it all gets logged in storage. Every generated solution, its score, the evaluation outputs, the feedback, it all gets stored. Think of it as the system's memory.
Building up a history of the search.
Exactly. And that history is crucial for the final component, the solution selector.
What's its job? Just pick the best one so far.
It's smarter than that. It looks at the whole history in storage and decides which solutions are most promising to focus on for the next round of generation. It might use evolutionary algorithms, like MOP elites they mentioned, to maintain diversity while still pushing through its better performance.
So it guides the search, prevents it from just randomly trying things.
Precisely. It selects the candidates that will be fed back into the prompt generator to kick off the next cycle. This whole loop, prompt, generate, evaluate, store, select, keeps running, iteratively improving the solutions.
And the paper emphasizes this loop is fast and cheap, hours and dollars, not weeks and person months.
That's the practical breakthrough. It makes this kind of automated discovery accessible. Okay, should we dive into the results? The case studies really show what this can do.
Yeah, let's do it. Start with that mixture of experts, the MOE inference one. What was the specific problem there?
So in large models like MOEs, you have different experts, smaller networks distributed across GPUs. When the model runs, you need to efficiently route data to the right expert. Balancing the load and placing these experts optimally is critical for performance.
And there was an existing way to do this.
Yeah, they had a baseline, a proprietary implementation. They took about 19.6 milliseconds for this expert placement task. Not terrible, but a bottleneck.
Okay, and OpenEvolve, their ADRS system, did what?
It blew it out of the water. The AI-generated solution ran the task in just 3.7 milliseconds.
Whoa.
That's the 5.0 back speed up. 5 times faster.
That's incredible. Was it just like a minor tweak the AI found?
Not at all. This is the fascinating part. The paper says the AI independently discovered a technique called staggered or zigzag tensor placement. It fundamentally changed how the data was organized and processed.
Oh.
It replaced slow, sequential Python for loops in the baseline with highly optimized parallel PyTorch tensor operations. A completely different algorithmic approach.
And you're sure it wasn't just copying something it saw online? Contamination from training data.
They argue is highly unlikely because the baseline they were improving upon was internal proprietary code. It wasn't out there for the LLM to have trained on. So it looks like genuine novel algorithm discovery by the AI.
Okay, that's a strong case. What about the second one, the cloud spot instances?
Right, this is about saving money in the cloud. Spot instances are way cheaper than regular on-demand VMs, but the cloud provider can snatch them back with little warning.
So the challenge is using them as much as possible to save cash, but without missing your job deadlines if they get reclaimed.
Exactly, a classic trade-off problem. In the standard setup, just using one cloud region, the best-known human design policy was something called uniform progress. ADRS managed to beat that, getting about 7% higher savings on average, sometimes up to 16.7% more.
Okay, so better than soda. But you mentioned a multi-region setting.
Yeah, and this is where it gets really interesting. Apparently, for the more complex case of balancing spot usage across multiple cloud regions simultaneously, there wasn't a good published algorithm. Humans hadn't really cracked it optimally yet.
So greenfield for the AI.
Pretty much. They compare the ADRS generated solution to a strong baseline policy tuned by hand. The AI solution achieved 26% lower cost.
26%. How did it manage that? What was the insight?
The Evolve policy used what they called an adaptive strategy. It basically learned to watch recent spot instance availability trends using a sliding window approach and dynamically adjusted how much risk it was willing to take.
So if spot instances seemed stable, it used more. If they looked shaky, it backed off.
Something like that. It adjusted its safety margin on the fly. And this helped it avoid a known problem with the single-region SOTA policy, something called a changeover trap.
Changeover trap?
Yeah, where the old policy would sometimes waste effort switching between different spot instance types too frequently if they're only available for short bursts. The adaptive strategy smoothed that out.
Clever. Okay, one more case study. Transaction scheduling.
This one's interesting because it showed two things. First, in the standard online setting where you have to schedule database transactions as they arrive,
Yes.
OpenEvolve actually rediscovered the known state-of-the-art algorithm, which is called shortest make span first, or SMF.
Okay, so it found the best known human solution could be contamination again, maybe. SMF is probably well documented.
Probably. But it still proves the system can reach that optimal point, even if it didn't strictly discover it this time. It shows reproductive capability.
But then they changed the problem slightly.
Exactly. They switched to an offline setting. Imagine you get a whole batch of transactions at once and need to schedule them all optimally. Apparently, there wasn't a great published solution specifically for this batch scenario.
And ADRS.
It found a new algorithm, an ON2 approach that reduced the total time to complete the batch, the make span, by 34% compared to just applying the online SMF algorithm naively.
34%, just by changing the setup from online to offline.
Yeah. And this highlights something really powerful for researchers, right? You tweak the problem constraints slightly, which happens all the time in the real world, and ADRS can rapidly explore that new space and potentially find a much better solution than just adapting the old one.
That's a really compelling set of results. It feels like this could genuinely change how research gets done, but it can't be perfect, right? What goes wrong? What are the failure modes?
Oh, definitely not perfect. The papers are good about outlining the pitfalls. They group them into three main types of failures users encountered.
Okay, what's the first type?
The simplest, runtime errors, your basic stuff. The generated code has syntax errors, it calls an API wrong, it runs out of memory, or maybe it hits the time limit or API quota you set for the evaluation. Just broken code.
Annoying, but fixable. What's next?
Search failures. These are more subtle. The search process itself goes wrong, like premature convergence, where the AI latches onto a suboptimal idea early on and just keeps refining that, never finding the truly good solutions.
Get stuck in a local minimum.
Exactly. Or they saw something they called stuck in the loop, which is almost funny. The LLM just keeps making trivial changes like renaming variables or adding comments without actually improving the algorithm's logic.
Wasting compute cycles.
Totally. And another one is mutation drift, where the changes become sort of random or contradictory over time, losing the coherence of the algorithm.
Okay, so runtime errors, search failures. What's the third category? This sounds like the dangerous one.
Yeah, algorithm failures. This is where the code runs fine, maybe even the search seems successful, but the resulting algorithm doesn't actually solve the problem you intended it to solve.
How does that happen?
Several ways. Misaligned objectives, the algorithm optimizes the metric you gave it, but maybe ignores a crucial constraint, like keep latency below 10 meters. It finds a super fast solution that violates the constraint.
Or overfitting, like in standard ML.
Yep. The algorithm works great on the specific workloads you used in the evaluator, but falls apart on slightly different real-world data. The test set wasn't diverse enough.
And the classic AI problem, reward hacking.
Ah, yes. The AI finds a clever loophole in your evaluation setup. It achieves a high score on the metric, but not by actually solving the core problem. Maybe it finds a way to make the timer run slower, or exploits some artifact in the simulator.
Okay, those sound like serious issues. So if you're a researcher or engineer wanting to actually use ADRS, what are the best practices to avoid these pitfalls? Let's start with setting up the prompt, the input.
Right, the prompt generator stage. Yeah. Garbage in, garbage out, basically. You need clear, structured specifications. Define the problem precisely. List the evaluation criteria and constraints. Specify the APIs the code needs to use.
Makes sense. What about the starting point, the initial code you give it?
This is interesting. They recommend not necessarily starting with the absolute best, most complex state-of-the-art code you have.
Really? Why not give it the best possible head start?
Because a super optimized complex SOTA code might actually limit the AI's ability to explore radically different approaches. It might just get stuck making tiny tweaks to that complex baseline.
I see.
Instead, they suggest seeding the process with a clean, minimal, but high-quality baseline, something simple that works correctly. This gives the AI more freedom to innovate structurally.
So, simpler starting point, better exploration potential. Anything else on the prompt side?
Tuning the level of abstraction. Think about what tools you let the AI use. If you give it access to very high-level libraries that already solve parts of the problem, it might just learn to call those libraries cleverly.
But it won't invent a new core algorithm.
Exactly. If you want genuine algorithmic innovation, you might need to restrict access to certain libraries, forcing the AI to build the logic from lower-level primitives.
Okay, careful prompting is key. What about on the other side? Preventing the AI from fooling the evaluator, avoiding overfitting and reward hacking.
Yeah. Evaluator design is critical. For overfitting, the main defense is diverse test sets. Don't just test one scenario. Include edge cases, different data distributions, maybe even adversarial examples designed to break simple strategies.
Make it robust.
Right. And for reward hacking, the key is multiple evaluation signals. Don't rely on a single performance number. Combine metrics. Measure correctness, efficiency, resource usage, maybe constraint violations separately.
So it can't just game one number.
Hopefully not. Using adversarial tests specifically designed to trigger known reward hacking patterns can also help. Make the evaluation tougher, more holistic.
Okay, this gives a much clearer picture of how to use ADRS effectively. Let's zoom out again. We've seen the power, the process, the pitfalls. What are the big picture implications here? What does this mean for the humans doing systems research?
Well, the paper's pretty clear. The role is shifting. If the AI can handle more of the iterative algorithm design and tuning loop,
The 40% we talked about earlier?
right, then human researchers need to move up the stack, so to speak. Focus on the higher leverage activities.
Exercise.
Problem formulation. Identifying the right problems to solve, understanding the real-world needs and constraints deeply. High-level ideation. Coming up with entirely new approaches or system architectures, maybe things the AI wouldn't think of initially. And strategic direction. Guiding the overall research agenda, deciding which avenues are worth exploring with these powerful new tools.
So the researcher becomes more like an architect, a strategist, and a critical reviewer of the AI's output.
Exactly. An advisor to the AI, in a sense.
Yeah.
Setting the goals, providing the crucial human insights, and validating the results.
But ADRS isn't magic yet. That paper also mentioned limitations, right? Where does it still fall short?
For sure, it's not a silver bullet. One major area is problems requiring non-isolated changes. Think about really complex distributed protocols, like Paxos or RAF for consensus.
Yeah, those involve intricate interactions across many different parts of the code, different modules, different nodes even.
Precisely. Current ADRS, especially with LLMs good at modifying localized code snippets, struggles to reason about and make coordinated changes across large, non-contiguous code bases effectively. It can't easily grasp the global implications of a change.
Okay, so complex distributed systems logic is still hard. What else?
Problems with weak verifiers. If you can't easily and reliably measure whether a proposed solution is better or even correct, then ADRS can't work. The verifier is the bedrock.
Can you give an example?
They mention things like trying to arbitrarily modify a database query plan. Proving that the modified plan is semantically equivalent and actually faster across all possible data is incredibly difficult. There isn't always a simple objective metric.
Gotcha. So if verification itself is a hard research problem, ADRS can't just automate it away.
Right. And the third big limitation is costly evaluations. If running your simulator or test bed for just one evaluation cycle is super expensive or takes a very long time.
Like training a deep learning model.
Yeah. Or they mentioned a weight compression example that took 12 hours per cycle. If one evaluation takes half a day, you can't run the thousands of iterations needed for the evolutionary search to be effective.
Yeah.
It defeats the purpose of acceleration.
So fast, reliable verification is absolutely essential. Given those limits, what are the big open challenges the paper throws out to the research community? Where do we need to improve ADRS?
Improving the evaluators is a big one. They need to be high fidelity, accurately reflect reality, general, cover diverse scenarios, and fast. That's a tough combination.
Any ideas on how to achieve that?
One suggestion is using cascading evaluators. Start with very fast, maybe less accurate cost models or simple checks to filter out obviously bad solutions quickly. Then, only run the promising candidates through progressively more expensive, higher fidelity simulators or real hardware tests.
A multi-stage filtering approach. Makes sense. What about the AI itself, the solution generator?
We need more agentic LLMs. Models that don't just modify isolated code snippets based on a prompt, but can actually navigate a complex code base, understand dependencies, read documentation, maybe even run debugging tools themselves.
Like a junior developer assistant, almost?
Sort of, yeah. An AI that can reason about the system more holistically and make more complex coordinated changes. That's a big step beyond current capabilities.
And the last challenge area?
Tuning objectives. Right now, we often have to boil down complex trade-offs, like speed versus fairness, or performance versus energy cost, into a single numerical score for the evaluator. But that's often really hard to get right.
How do you put a number on fairness?
Exactly. So the paper suggests exploring things like preference learning or inverse reinforcement learning. Instead of the human defining the score function perfectly up front,
The AI learns it.
it learns the human's preferences by observing which solutions the human researcher flags as good or better among the ones generated. The system could infer the underlying objectives from human feedback, which might be easier than writing down the perfect formula.
Interesting. Letting the human guide the objective function itself.
Could be a more natural way to handle those fuzzy, multi-objective problems.
Okay, so wrapping this up, Barbarians at the gate. It sounds like less of a warning and more of a statement of arrival.
I think so. It's making a strong case, with evidence, that AI-driven research for systems is not science fiction. It's here, it works, and it's already achieving SOTA results on non-trivial problems.
And the really mind-bending part is the feedback loop.
The virtuous cycle. That's maybe the most profound point. We can use ADRS today to build better AI systems, faster training, more efficient inference, better resource management.
Which then makes the next generation of ADRS tools even more powerful.
Exactly. It could lead to this compounding acceleration of discovery, specifically driven by the systems community building better tools for itself faster than ever before.
So the final thought the paper leaves us with, really, is a challenge to the community, to you, the listener. We now have this nascent capability to automate algorithm discovery.
A new superpower, almost.
Right. So the question is, how are you going to wield it? What new, harder, previously unthinkable computing challenges can we now define and tackle because this automation is becoming available?
That's the big question. A lot to think about.
Definitely. Thanks for joining us for this deep dive on AI Paper Podcasts.
See you this time.